Okay, so now we're going to discuss the light path again, use our knowledge on even graphs, namely decomposition of a graph into even graphs. We'll use our results from there to solve this problem called the light path gain. Okay. So what we have is a graph, and on the graph, each vertex has status, has a light. So status of light is either on or off. So here, triangle, red triangle indicates the light is on. So here, these three are on, these three are off. Here, these two are on, these four are off. All right. So what we can do is, regard each vertex as a switch, as a button, we can push it. Once we push the vertex, then the status of the vertex and our vertex in its neighbor will change from on to off and from off to on. All right. So if we push this vertex, so let's see. If I push this vertex, what happens? Status of its neighbor changes. So this one will be off, this one will be on. So I use different light. So this one on, this one on, this one on. And then this one is also off if I push this vertex. So this one will be on. So after this, new status will be on, and off, off. All right. So this one will be gone. This one will be gone. This one will be gone. All right. So the vertex we push will also change its status. So if we push this vertex here, light will be on. So this light of this vertex will be on. And these will be on. And these two will be off. So after we push this vertex, this one happens. All right. So our objective is to push vertices so that eventually all lights will be off. Okay, so that's the objective of the game. For convenience, I think it's we'll use so-called closed neighborhood. Use this notation. So use this notation to denote vertex together with its neighborhood. So if this vertex V, closed neighborhood will be all these vertices for the ball, contain all vertices. Its neighbor together with itself. Right? So let's see. When will the status of vertex change? When the status of vertex V will change. Now, if we push vertex twice, then status will come back. If it's on, then off, then on, right? So in order for vertex to change its status, we push vertices inside the closed neighborhood. NV all the number of times. You push it all the number of times. So, for example, if I want to change the status of this vertex B, all right. So I can push this vertex. So that's what, that's all the number of times. Or its neighbor, I push all the number of its neighbors, all the number of times. Then we change the status. For example, if I push this vertex, then one. Push this vertex, the status will change to on. If I push another vertex, so this one, second time I push this vertex, then status change back to none. Then if I push this vertex, then this one will be on. So all the number of times the status will change. If even number of times, there's no change. All right. So only if we push number of vertices, all the number of times. So no change of status if even number of times. the status of vertex will change only if and only if number of times we push its closed neighbor from this closed neighbor. Because vertex itself also counts all the number of times. All right, that's very important. So that we see when the status will change. Secondly, ordering actually does not matter. How we push it up because cancel. If we push it once, twice, 3 times, 4 times, actually it will cancel. So really, what's important is the number of times we push. Actually, not important. The parity. How many times we push a button actually is not important. Rather, it's a parity. Whether it's odd number of times or even number of times. All right. So that determines whether status change or not. And ordering actually does not matter. Eventually, what happens is we partition verses into 2 parts. So the second thing you need to observe is ordering does not matter. So the game looks to be dynamic. We push vertex one by one, but actually it's not. It's not dynamic. It's a vertex partition problem. All right. Actually, it's a vertex partition problem. So eventually what happens is we partition vertex sets to be 2 parts. Actually, eventually it's a vertex partition problem. We partition vertex into 2 parts. So say these parts denote vertices have been pushed. So these are pushed vertices. So here unpushed. So these are vertices not pushed. All right. So eventually that's what happens. We have a vertex here with each vertex on this side have been pushed. Each vertex on this side has not been pushed. All right. Now let's take a look on when vertices will change its status. So for this side, from vertices that have not been pushed, really depends the degree to that side. So if this vertex adjacent to an odd number of vertices, so let's just use 1 odd number of vertices. So if vertex degree here, let's say B, if vertex degree is odd, then the status will change. The status, let's say, status change will be yes, because once I push this vertex, the status of this vertex will be changed. All right. Now, if I change it to even number of vertices on this side, this one is even. So it's even. Because once I push this one, the status change. Once I push this one, status will change back. So no change. So here status no change. All right. So for vertices on this side, the degree to this degree determine when the status will change or not. If it's odd, then change. If even, it will not change. Now look at this side. For vertices on this side, they have nothing to do with these vertices at all, because only these vertices are pushed. So whether status change or not depends on number of vertices are neighbors of a vertex here. Say consider this vertex in U. Whether it changes depends on number of vertices in its close neighborhood. So if it's adjacent to all the number of vertices. So 6 degree, maybe I should write for this one. Maybe change a little bit. So refer to that side, maybe use degree, please okay. So refer to this degree. Okay. So here also refer to this degree. This degree, so inside use V star U. So degree has two possibilities. One is odd, one is even. Again, depends on this one. Now, when its degree is odd, when degree odd, number of vertices in its close neighborhood actually is even. This one, when it's odd, actually no change. So this is situation odd, 1. All right. So actually number of vertices inside the close neighborhood is 2. So there's no change. When it's even, so for example, this vertex, when it's even, so this vertex, all right. So closed neighborhood actually contain all the number of vertices. So in 1, 2, 3, they actually change. So it's just the reverse as complementary to this part. This part all the change, even no change. Here all the no change, even change. All right. So eventually it's a vertex partition problem. Okay. Really depends on degree of these vertices to this height and vertices degree in this induced subgraph that determine whether status of vertex will change or not. Applying status. All right. So then you get a feeling of how this game works. Now let's consider a special case to illustrate the idea how it works by using our results from a vertex partition of a graph into 2 even induced subgraphs. So let's consider the following special case. Initially, all lights are on. I will use one example to illustrate it. So let's see. Okay, let's see the graph look like this. Okay, that's our graph. All right, so initially all lights are on. So we consider this special case. All lights are on initially. Remember, once we push a button, then lights will be off. So it's not really easy. All right. After we push a few buttons, it's become complicated. Initially, we assume all lights are on, and we want to turn off all lights. So what we are going to do is construct a new graph. I add one vertex, one particular vertex, called x. All right. What we do is the construction is as follows. For each vertex of even degree, we add an edge between vertex and x. All right. That's what we're going to do. So in this graph, let's see. Degree 3. So this one is degree 3. Okay. So let's use the 1 to denote its degree is odd. 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 0 to denote degree even. So 2, 4, and 2. All right. So for vertex labeled 0, we add an edge between vertex and this particular vertex. So just add 3 new edges. So we'll go from here, here, and here. That's our graph. All right. Now, by our previous results, this graph certainly contains odd degree vertices because we make these vertices to be odd degree. The remaining vertices are also odd degree. The actual graph contains an even number of odd degree vertices, even number of vertices in this particular case. All right. So then it has a partition into 2 induced even graphs. So this one has a partition. non-infinite partition of two even supergraphs. All right, none of them are empty. So for this particular case, okay, let me see. This one. It's a C3, a triangle. So it's even graph. Outside is a 5 cycle. 1, 2, 3, 4, 5. Another part is this part. So it's vertex partition. So that's one part, another part. All right. So let's say we start. And then outside. So we have a partition, vertex partition. Both of them are even graph. So this one is even supergraph. This one also induces even graph. It's C5, exactly C5, no cost. That's what happened. Let me erase something, otherwise too messy. Erase everything. And now it's easy to see. So the V star is this part, and the remaining part, this part, is a V minus V star. It's also an even graph. C degree 2 for each vertex in this part. In this part. So we have two graphs. Suppose even graphs. Okay. All right. All right. Now what happens is we use this set as vertices that will be pushed. So this set is a push set. So we push every vertex inside. Outside, we do not push at all. So it remains to show that once we push these vertices, all lights will be off. So how this is the case. Now, first look at vertex inside. Inside, each vertex has even degree because this graph is even. So for each vertex inside V star, for each vertex, so V star is a set that not contain X. Okay, V star is a set that not contain this particular vertex. Now for each vertex inside the V star, because this one is an even graph, degree of V is even. In this graph, degree is even. Now, central neighborhood of V, let me write in this one. In this graph, close neighborhood of V, because degree is even, the first vertex itself, this one is odd. The parity of this one is odd. This number is always odd. Because all these vertices are pushed, we pushed it odd number of times. Therefore, vertex status of every vertex here will be changed. So initially, it's lights on. Once we push all these three vertices, lights will be off. So all of them, lights will be off. When I put, so if you want to look at the order is X cubed. When I push this vertex, that one will be off, right? This one off, this one is off. When I push this vertex, if you want to look at order, when I push this vertex, lights off. Now when I push this vertex, lights will be on. This one will be on, this one will be on. Now when I push this vertex, then this one will be off, this one off, this one is off. In this particular case, it happens to be a triangle. If it's 5 cycles, it will not happen simultaneously, right? Because in this case, it happens to be a triangle. So it's a clique. So they happen simultaneously. All right. So element here will be off. Now for vertices outside, let's take a look. Initially lights are off. Lights are on. Okay. Initially for these vertices. Okay. Now look at vertex that we do not add an edge between vertex and x. So degree will be off. So for example, this vertex, degree is off. This particular vertex is off. Right? Now in this graph, vertex degree is even. Inside this graph, vertex degree of u is even because that's an even graph. So that means degree, this one connected to an odd number of vertices inside the V prime. So this number, this is odd number. All right. So we push, when we push all vertices here, an odd number of vertices will be adjacent to this one. All of them are pushed. Therefore, the status of this one will be changed. Remember, we don't push these vertices at all. Only push vertices inside here. So this one lights will be off because it's stable push all the number of times. So it may be odd number of times. So this one, this one, this one. Okay. So according to this particular case, it's a degree is one. We just push this vertex. We change the status. All right. But in general, it's odd number of times. Okay. Now we do not add an edge between u and x. So this one will be okay. Now consider vertex. We add an edge between this vertex, the u prime, maybe use a different name. Let's say y and x. All right. So then degree of this one initially is even. Degree dy is even. That's the reason we add this edge. Okay. Now the degree inside this graph is always even. Originally degree is even. Once we add this one, degree becomes odd. Once we add this one, degree becomes odd. So odd minus even. So that means they're odd, again, odd number of vertices inside here will be adjacent to this one. Because once we add this one, degree becomes odd. So this part is even, so this part must be odd. Again, so in this particular case, the one. Once we push this one, the status will change from on to off. So in general, there will be odd number of vertices. So there will be odd number of vertices, maybe 3. So once we push it 3 times, the status of this one of course change because odd number of times. Even number of times, change back. But odd number of times it will change. So this status will be changed. So initially it's on, so now it become off. Okay. So for vertices on B minus B, there are only 2 types of vertices. Vertices initially odd degree, vertices initially even degree. So we show that with an odd, status will change. When it's even, status will also change. So therefore, all vertices here, the lights will be off. All vertices here, lights will be off as well. Of course, this is not a vertex in the original part. We don't need to care about this one. Okay. So you see that we can use partition of a graph into 2 even graphs. Then use this partition to define the set to be pushed. That's the part that will not contain this particular vertex. Okay. So once we push all vertices here, then status of every vertex will be changing from on to off. So this one is an application of how we use this vertex partition theorem in connection with even graphs to solve the light out game. But actually, to verify the set is not easy at all. To find such a partition is not trivial at all. It's very complicated. It's difficult. Even if I give you a graph, I know there are solutions, but it's not easy. It's always a solution, but it's not easy to find such a partition. Not easy at all. It's actually Really very difficult. Okay. All right. So there are lots of in the internet you can find different versions of Lighthouse games. So if you want to have fun, you can try it out to get a feeling of how it works. There are many, okay, online one, or you can download them. Okay, so have fun with this game. But keep in mind that the underlying mathematics actually is the graph theory in connection with even graphs, right? Okay.